We will now pause for a short review of the material just discussed. A truth table is used to illustrate the operating conditions of a given gate circuit. It will list all the various input and output combinations. The AND gate is only high at the output when all inputs are high. Essentially, we are saying when one input is high and all of the other inputs are high, it produces a high output. The OR gate, on the other hand, will produce a high at the output when any of the inputs are high. In other words, if one input or any of the inputs are high, it will produce a high at the output. The inverter gate, or NOT gate as it is sometimes called, is used to switch the signal from one state to the other. The NAND gate may be considered as being an AND gate followed by an inverter gate. The NAND gate symbol is distinguished by the small circle placed at the output end of the AND device. The NOR gate may be considered as being an OR gate followed by an inverter gate. The NOR gate symbol is recognized again by the small circle placed at the output end of the OR gate. Only two states of energy exist in a digital logic circuit. These two states may be referred to as being either high or low, on or off, true or false, or 0 or 1. The 0 represents a low state and the 1 a high state. Common gate circuits are also available with multiple inputs. These gates operate on the same principles as their two input counterparts. This concludes our first review. Here we see two more commonly used gates which are referred to as exclusive logic gates. Shown on the left is the exclusive OR gate, and shown on the right is the exclusive NOR gate. Notice the letters used to designate each gate. The first gate we shall observe is the exclusive OR gate. The exclusive OR gate is the most widely used in the exclusive logic family. This gate is used frequently in digital arithmetic circuits. Here we see an equivalent circuit of the exclusive OR gate. Notice that it consists of two inverters, two AND gates, and one OR gate. Let's examine the logic combinations of this gate. We will begin with both inputs in a low state of energy. When we apply a low on input A, it gives us a low on 1/2 of gate A and a high on 1/2 of gate B. This is because the low signal being applied to gate B had to go through an inverter before it reached the input of the gate. We also said that input B was low, so this gives us a low on the other half of gate B and a high on the bottom half of gate A. Remember, the inverter on gate A changed the low to a high before gate A received the signal. We now have a low signal and a high signal being applied at gate A. Since this is an AND gate, we know that a low signal and a high signal will produce a low output. Gate B also has a low signal and a high signal being applied at its inputs as well, therefore it will also have a low output. The low outputs from the two AND gates are then fed into an OR gate. As you will recall, two low inputs on the OR gate produced a low output. By referring to the truth table, you can see that a low on input A and a low on input B will produce a low at output C. Now let's see what happens if we make input B high while leaving input A low. The truth table shows that it should produce a high output from the device. We have already seen that a low on input A produces a low on 1/2 of gate A and a high on 1/2 of gate B. And when we apply a high on input B, it gives us a high on the second half of gate B and a low on the second half of gate A. This gives us two lows at the inputs of gate A and two highs at the inputs of gate B. Since gates A and B are both AND gates, we will have a low at the output of gate A and a high at the output of gate B. The OR gate, being fed by the two AND gates, now has a low from gate A and a high from gate B being fed into its inputs. Remember, if the OR gate has one input or the other, or both of its inputs high, then it will produce a high output. As you notice, this is in accordance with the truth table logic. Next, we will make input A high and input B low. Our truth table shows that there will be a high output at C. We will now see how this happens. When a high is applied at input A, it feeds a high into 1/2 of gate A and a low into 1/2 of gate B. When the low signal is applied at input B, it feeds a low into the second half of gate B and a high into the second half of gate A. Since gate A has 2 high inputs, it produces a high output, and since gate B has 2 low inputs, it produces a low output. This OR gate being fed by the 2 AND gates now sees a high and a low signal at its inputs. This causes the OR gate to produce a high output. As you can now see, a high at input A and a low at input B produced a high at output C. Now let's see what happens when we place a high at both inputs A and B. As you notice, the truth table shows there will be a low output. When input A is made high, it feeds a high signal into gate A and a low signal into gate B. And when input B is made high, it feeds the second half of gate B with a high signal and the second half of gate A with a low signal. Since gate A has a high input signal and a low input signal, it produces a low at the output. In the same respect, gate B will also produce a low output since it also has 1 high input and 1 low input. The 2 low inputs being fed into the OR gate will produce a low output, as you will notice on the truth table. You may have also noticed that the exclusive OR gate has a special characteristic of producing a low output with both input signals are the same. Next, we will examine the exclusive NOR gate. Here we see the equivalent circuit of the exclusive NOR gate. This circuit also uses 2 inverters, 2 AND gates, and 1 OR gate. As you can see from the truth table, when both inputs A and B are low, it produces a high at the output. To understand how this happens, we shall examine the equivalent circuit. When input A is low, the signal is fed into 1/2 of gate B and into the inverter circuit before going into gate A. This changes the low into a high before going into gate A. When input B is made low, it is also fed into 1/2 of gate B, and it also goes into an inverter circuit before going into gate A. Once again, the signal is changed into a high before going into gate A. Since gate A has 2 high inputs, it produces a high output. Gate B, on the other hand, has 2 low inputs, so it will produce a low output. When the OR gate sees a high input and a low input, it switches to a high state. As you see, we have proven that 2 low inputs will produce a high at the output, as was shown on the truth table. Next, we will examine the condition of the exclusive NOR gate when a low is applied at input A and a high is applied at input B. The truth table shows that the output will be low. As we have just seen, when input A is made low, it places a high at one input of gate A and a low at one input of gate B. But when input B is made high, it places a high at the other input of gate B and a low on the second input of gate A. The high and the low inputs being applied on gate A will force the gate to go to a low state since it is an AND gate. Gate B will also be low since it also has a low and a high input being applied. The OR gate now sees 2 low signals being applied at its inputs. Therefore, it will go to a low state. As you see, once again, the truth table was correct. Now let's examine the condition of a high at input A and a low at input B. According to our truth table, the output will be a low. When input A is made high, it feeds a high into 1/2 of gate B and a high into the inverter circuit at gate A. The inverter changes the signal into a low and feeds it into gate A. And when input B is made low, it places a low on the second input of gate B and a high on the second input of gate A. Remember, the signal first passes through an inverter circuit before reaching gate A. Since gates A and B are both AND gates, and they each have a high and low signal being applied at their inputs, they will produce a low at their outputs. The low signals from the AND gates are then fed into the inputs of the OR gate. This causes the OR gate to produce a low output, once again just as was indicated by the truth table. Next we shall see what happens when we make both inputs high. Our truth table shows that there will be a high output. As you can see, when input A is made high, It places a low at one input of gate A and a high at one input of gate B. When input B is made high, it feeds a high into the other input of gate B and a low into the other input of gate A. Gate A now has two low inputs, which causes it to produce a low at its output, and gate B now has two high inputs, which it causes it to produce a high output. This high output from gate B and low output from gate A is then fed into the OR gate. This causes the output of the OR gate to develop a high. There are many different types of logic families, each having its own particular characteristics. When designing these logic circuits, there is always a trade-off between switching speed and the power consumed. Notice, for example, that the emitter-coupled logic family is the fastest of the logic groups. It has a switching speed of only 1 to 2 nanoseconds, yet it will consume 40 milliwatts of power. Whereas the CMOS logic family has a switching speed of 25 nanoseconds and only consumes 10 nanowatts of power. This table was shown to you so you will become aware of and familiar with the different logic families that are used in various digital circuits. As you have noticed, each family has its own special combination of operating parameters which make them useful in specific types of applications. The exclusive OR gate is another commonly found gate used in digital arithmetic circuits. The uniqueness of the exclusive OR gate is in its ability to produce a low output state when both inputs are at the same energy level. The letters XOR are often used to designate this gate circuit. To better understand the operation of the exclusive OR gate, you should use the equivalent circuit shown to you earlier in the program. If you will remember, this circuit consists of two AND gates, two inverter gates, and one OR gate. The exclusive NOR gate is another commonly found gate circuit used in digital arithmetic circuits. The exclusive NOR gate differs from the exclusive OR gate in that there is an inverter gate placed at its output. This causes the output to go high when both inputs are of the same state of energy. The letters XNOR are often used to designate the exclusive NOR gate circuit. To better understand the logic operation of the exclusive NOR gate, it is recommended that you study its equivalent circuit. As you can see, it also uses two inverter gates, two AND gates, and one OR gate. Notice also that the inverter gates are placed at both inputs of gate A. There are a wide variety of digital logic families which have been used or are currently being used in today's modern equipment. Each family has its own special characteristics and parameters. This concludes review number 2.